Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Why don't we get started? I think we've given people the customary grace period. So I'm very pleased to introduce David Weatherall, who's visiting us from the University of Washington. I think David is well known to almost everyone in the room. I think we've known David ever since he was at MIT, and we've been interacting with him in the years since then. But now he's going to be telling us about some more recent research. Some things that have been going on, I guess, in collaboration with folks at the Intel Research Lablet and folks at UW. So without further ado, David.
Okay. Thanks very much, Rich. Well, it's a pleasure to be here. Thank you for coming. I'm very happy to be here. Well, I'd like to talk to you today. I'm going to tell you about some of the cool things you can do with RFID technology, basically. You know, I'm only over the other side of the lake, but it's been years since I gave a talk here, many years actually. Okay, so this is me in a nutshell, at least as you would gather from the titles of my publications. I'm interested in pretty much everything to do with networks, and I've worked on network systems fairly broadly. In particular, I've sort of worked in internet privacy and security, all the way from internet denial of service through to privacy issues today on the web and on mobile phones. I've done a lot of work on internet measurement, understanding the performance of different paths, ISP mapping, and so forth, and then wireless and mobile systems, 8 to 11 different kinds of perceptual apps these days, and all of that. Come right on in, seats at the front if you're short. Yeah. So I think those are all interesting areas, and there's a lot of great future work to do there that's particularly relevant to Microsoft. But I'm not going to talk to you about that today. Instead, today, I'm going to talk to you about some other work that I've been working on in the area of ubiquitous computing and RFID systems, if you like. Don't think of this as sort of future work that needs to be directly relevant to you. I hope you'll take this as an area that is probably fresh for most of you. I hope you'll find it to be an interesting area in which there'll be a lot more activity in the future. And it's also sort of indicative of a fairly broad body of research that I've been up to for the past while. Okay, so here's the topic area that I'm going to talk about today. It's the Internet of Things. Now, the Internet of Things is a pretty broad and somewhat vague vision for network systems that have been extended into the everyday objects. Think light bulbs, tanks, toasters, whatever you like. All of these different objects that we might use in our everyday life, maybe not tanks, but other things, are really connected as part of the computing and networking substrate in some ways. This is not a new vision. This is a vision that's been around and evolving since around about 2000. Here's a typical paper that you could read, maybe a good one early on. Gershenfeld's article on an Internet of Things. This really sort of proposes an Internet 0 in contrast to an Internet 2, rather than speeding up, slowing down, and going everywhere. Now, the Internet of Things is sort of associated with two other topic areas that we're going to sort of hear about today. One is just RFID technology. In fact, the vision is really attributed to the early formation of the MIT Auto ID Center, out of which sprang EPC Global, and that's the body that standardizes UHF RFID tags, the electronic product codes of today, which are now beginning to take off. So RFID is a key technology here for reaching out to all of these everyday objects. The Internet of Things is also pretty closely associated with ubiquitous computing. You've got to have some reason to kind of put all of these tags on objects, and the presumption here is that there will be ubiquitous computing style applications in the sort of classic Mark Weiser sense of having technologies that are disappearing into all of the objects around the world, and accomplishing all sorts of other applications where we interact with rooms and smart environments and objects much more naturally. Okay, so this is the space. It's another publication in Scientific American. I'm sort of realizing, I don't know about you, but maybe I've overlooked a venue here for Vision Papers. So this is a fairly broad and vague vision, the Internet of Things. What I would like to talk to you about today, really, is our view of the Internet of Things and work that we have done and progress that we have made over the past small number of years to work towards that vision. In particular, I'm going to talk to you about some of the technology you can use to build your own, Internet of Things, some of the different applications that we have explored, some of the systems and networking issues that we've tackled and continue to tackle to build those new applications and drive the technology forward, and also the community that we've been building. And this progression also sort of parallels just where we worked over time, from an early focus on just some of the technology and being able to get anything going, through to some of the systems issues that we're just really beginning to tackle now. A lot of other people besides myself have worked on all of this material. And in particular, I would like to credit, Intel Labs and the University of Washington, essentially. This work, most of this work, occurred when I was running Intel Labs Seattle, and it's also joint with University of Washington. And it's now, most of it's really being moved over to the University of Washington. In particular, we use some hardware here, the WISP, that I'm going to tell you about in a little while. Josh Smith is really the PI on the WISP, and some of you might know him. If you don't, he's a great guy to talk to. You should talk to him. He is now faculty at UW as of about February. So he moved from Intel to UW. And you see that there are other people there, UW students as well as Intel engineers have been building some of this technology. Most of what I've been doing with this technology is on the reader side and building the system, some of the software issues on these WISPs, and actually building complete applications. And in particular, I guess I would single out Josh, Alanson, and Michael Buettner. Michael Buettner is my student, and Alanson is Josh's student at UW, as well as a number of other people have contributed to all of this. And I've co-authored papers with all of these people. Okay, so this is really my outline for the talk, those 4 points. Let me just dive into it. And I'll take questions whenever, if anything's not clear, just go for it. So technology. We want to build an Internet of Things. What do we do? Well, you can't just use any old technology. If we're really going to push the internet or connectivity out into the everyday world, we really need technology, which is small, inexpensive, wireless, and long-lived. If you don't have those characteristics, it's going to be very difficult to deploy it ubiquitously everywhere. At the same time, you need more than just a barcode or something on objects. We would really like some fairly rich sensing capabilities and even controls of different kinds, as well as the traditional computation, storage, and communication. It's only by adding sensing to the mix that you really get to write rich applications which understand what's going on in the real world and have a chance of telling people what to do or altering things in some way. Now, the interesting observation here really is that some of the different technologies provide almost some of the ingredients. RFID technology provides a lot of what you would need to get bullet point 1. Sensor networks provides a lot of what you would need for the second. We'd like to get the best of both. And I'm sort of loosely calling that RFID sensor networks. Other people have called this computational RFID. I don't really like either name, actually. Computational RFID is a little off because it doesn't talk about the importance of sensing. But not only do we want the best of both, but we also want to throw out some bits of these technologies to make it work well. So let me just go through quickly some sensor network and RFID, at a high level, and sort of say what we want to keep and what we don't want to keep in terms of the features. Here's some classic wireless sensor networks. I'm sure many of you are experts on this material. The notion here is that you put sensors on everyday life, as I've been describing, so it seems like a good fit, really to monitor and enable different kinds of smart environments. And the applications that have been explored here, particularly over on the academic space, are all of the ones everything from monitoring your habitat, seeing what's happening with those birds, into hospitals and homes for different kinds of smart environments, on either the environments or on bits of the objects. To make all of this happen, there are some sort of key features. You have small sensor nodes that are placed around the environment. There's a typical one. This is maybe a little dated, but it's Telos Moat. And this collection of devices, these are all small devices, but they're not that small in some sense. They're battery powered, right? So a lot of what you can see on there are some of the batteries. They communicate often in a peer-to-peer fashion across one another via a chain here, and they send fairly rich data. Okay? But I think it would be fair to say, even though there's been a huge number of academic publications in the area, that on the business side, the market for these kind of traditional sensor network applications has been fairly small. And in fact, even in the academic space, many people now are looking towards mobile phones and cars and so forth as really the new kinds of sensor networks for participatory sensing, if you like. Okay, that's sensor networks. On the other hand, let's look at RFID. So I'm mostly interested in classic UHF RFID technology. There are actually many kinds of RFID. In some ways, it's almost the opposite of the academic sensor networks, in that it was strongly motivated by business needs. And RFID has been applied a lot, really, to inventories and supply chain management and so forth. Just sort of think, identification, electronic product codes, if you like. So all of these different kinds of RFID differ a lot in their capabilities and their technical characteristics. You sort of go from active RFIDs, and these are the small things that are almost like, motes. They can have batteries, they can communicate over a fairly reasonable range. They're not that cheap. Stick it on your shipping container, your truck or your cow, just to make sure you know where they are. On the other hand, there's very different RFID technology too. Technology many of you must be familiar with is passive high-frequency RFID. Operates around 13 megahertz. It usually has a very short range. We're talking centimeters because it uses induction to power things. It's passive, so there's no battery. So it's using induction and power from a reader to be able to power these cards. You'd find these in, smart cards. In fact, I probably have a card in my pocket, right? This is high-frequency passive RFID. Okay, but the kind of RFID I'm really interested in is passive UHF RFID. This runs on an ISM band around 900 megahertz. This is interesting because it has those properties of being very small and cheap, because think of it really as a sticker, right? No batteries, no nothing, and it's small. Yet you can read it at a reasonably large range, 30 feet. Maybe we could cover this room sort of and find where all of the objects are in this room. You don't need to place them right on a reader. And this was really, there was a lot of attention on UHF RFID following, the Walmart rollout, or at least attempted rollout, when they decided that all of their suppliers would place UHF RFID tags on all of the pallets that were arriving, or even smaller units that were arriving at their stores. This, of course, as many of you know, didn't happen very well. It's taken a long time to roll out for many reasons that I'm not going to go into, business reasons as well as technical reasons. And the industry has sort of always had wanted to produce tags in the sub 5 cent range. This is somewhat unrealistic. It's not the case today. It's actually very hard to give you any pricing data on RFID tags. It depends whether you want to buy 100 or 100 million. Things are very much up in the air. But generally, people believe that this low price point hasn't quite been reached. Nonetheless, they're really very inexpensive compared to buying a mote or buying anything else. I guess I'm sort of drifting into some of the features of how they work. Let me tell you a little bit about that, because that matters really for the rest of my talk. I assume most of you sort of know how sensor networks work, but many of you will not necessarily know how RFID works. It's a different kind of technology. Okay, so instead of a peer-to-peer setting, we really have a different setting here where you have a reader that is in control. That has all of the intelligence, and then the RFID tags are simple. These tags, RFID tags, really, there's the silicon for it, that tiny dot. All of the rest of the tag is just the antenna, right? So they're going to need to be physically that big just for an antenna to pick up a little bit of signal. These are passive. What happens is that the reader sends out a signal, quite a large one, up to 4 watts, EIRP. It transmits. That signal can be literally reflected off the tag. It's radar, basically. What the tag can do is modulate. It can change its reflection coefficient to either reflect back some of the energy or to absorb it. And thereby it can kind of modulate a signal which can be detected at the reader. This is called backscatter communication. So it's very low power. It's not even a real transmission by the tag. You're just not going to get a lower power method of communicating, at least on the tag end. And the range depends on technology and just how well you can receive signals, but 30 feet is quite reasonable. You'll even get it to be a little higher. And the tags are usually just identifiers. The main standard for UHF RFID is the so-called EPC Gen 2. EPC stands for Electronic Product Code. It's an ID that you stick on things instead of a barcode. And Gen 2 is just sort of where they're at. It's the version of the technology. The deployment of these systems has been fairly slow, actually. And there are many reasons for this, business reasons and so forth, as I mentioned. But from the point of view of this talk, I think one thing that's interesting that I would claim is that to be useful, they really need to add value over barcodes. Otherwise, it's difficult to charge any more than a barcode. And so that's really what we're going to try and do with the Internet of Things. Somewhat ironically, I guess, it looks like UHF RFID technology deployment is now beginning to take off. This could be the year of RFID. I think they expect, sales of the of these kind of tags to reach 1 billion this year. Yeah.
As I understood, Walmart was the big push of this, right? They required all the suppliers to use it. Do you know what their motivation was over barcode? Why they were convinced?
Oh, they wanted to save money and provide new functionality and be able to, well, I mean, it's all business reasons. It is to save money. The tags need to be fairly cheap to do that. The main value proposition is item level tagging. So if you imagine a store, here's the classic scenarios like the Gap, and you go in and you say, I want a pair of jeans, size 34 or whatever. It's a big pile of things. Do they have your size or not? Some salesperson goes through and sorts everything. If you have RFID and you can really tag things at item level, you know what you have around the store and where it is and that it's over there and so forth. That's worth a lot. It also turns out to be the case that barcodes don't... I sort of learned a fair bit about this actually talking to some of the people at MIT who drove around forklifts and worked with Walmart a lot and kind of ran into a lot of the problems. But it also turns out the barcodes actually aren't that accurate for maintaining your inventory. And the reason is, when people check things out, you'll have, a dozen different yogurts of all sorts of something, and the salesperson will grab one and just scan it 12 times and you're done. This and a bunch of other things when they can't read it mean that, the databases of what inventory you actually have is often, quite off. And knowing it accurately is truly worth a lot of money to businesses. So the idea is that by electronically tagging everything, you really will be able to get an accurate picture. We've just got to make the technology work. Okay? But I want to go beyond simply tagging objects and knowing inventory, right? I mean, that's very much where we're focusing. And the fusion of these technologies that we're looking at for RFID sensor networks is this picture. Now, in this picture, I've started from an RFID base because that's actually closest to what we need, I think. If you really want to be able to tag objects with things which are inexpensive, wireless, long-lived, small, and all of this, RFID technology is a great base. But we need to add things to RFID technology. So you can see in this picture I've replaced RFID tags with things we're calling WISPs, wireless identification and sensing platforms. So these are now small computer platforms. It's not a fixed function tag that just returns an identifier and has another state machine for storing things. Yes?
What does that do to the cost per entity?
The cost?
The cost.
The cost will go up a lot. What will it be when it's, well, I would argue that's okay because they'll actually provide a lot more value. What would the cost be when these things are manufactured? I have no idea. We have prototypes. The BOM for the prototypes is around $100. Now, it's all just, goes down to that much silicon when you fabricate it. In theory, the cost for these things should be no different than the cost for RFID tags, modulo some of the sensors. And there are actually packaging challenges in getting all of this down. Yeah. So that's a nice point. Haven't got there yet. Okay, so these WISPs, think of them as just small computers. We're going to program them, basically. They run application code, they perform sensing tasks, and have different kinds of sensors. That means they send rich data back to the readers, not simply identifiers. That means, our reader is now something that's a little more general than we had before. These readers really are there to provide power to all of the tags. It's still the RFID model. The tag can't do anything by itself. The reader's sending power that the tag is gathering and then using to be able to communicate and so forth. But these readers, think of them much more ideally as gateways to the internet where other application code is running. Have much more of a, this should begin to look more like an internet style system. So this is the sort of combination we want. And I'm sort of arguing really that taking this view of the technology is going to give us the advantages we want to realize an Internet of Things. Now this picture, this mishmash of technology is not hypothetical. It's not a question of, well, could you do this? Could you actually turn these passive tags into compute platforms? You certainly can, because it's been done. Yes?
Maybe I'm asking ahead of time. Do you have energy storage component on the device, or it only sends when you are reading it?
Very limited energy storage. A small capacitor, which is basically, orders of magnitude less than a battery on a moat, and it's enough to kind of balance the incoming power and the outgoing power, just to get you over humps.
You're reading it.
Yes, that's right.
Do you see limitations in terms of application side?
Ultimately, yes. And you'll see we've explored some applications where you add a little bit of energy storage. But it looks like there are many applications that you could do without long-term energy stores. And that's because a model for all of these readers is that they're always on, and right? They're always kind of asking on and powering and asking tags to do things. And that works for a lot of applications. Yeah, Chichi.
So the question is, what do you need computation on this node, compute on this node? is it mostly to like get the readings from the sensor and send it back, or is it for doing something else as well?
Let me. We'll get to applications in a while, but here's a quick example. Maybe you only want to. Maybe you have accelerometers and you only want something to send messages back to you when it starts moving. It would be processing all of those samples and deciding if it's moving or not. That is a small program, and it would only decide to communicate to tell you that an object's actually in motion. You can't do that with traditional RFID or without computation to filter all of the sensor values in some way.
I think what I'm asking is, can you get, if you had no microcontroller, can you still have some sensors? I'm not sure if that's even the right question.
You can have some sensors, and I would say that they're probably not very useful for applications because all you can do is hardwire functionality to send sensor values back. Right? I think the compute probably adds a lot of value.
So why can't you just do all the processing on the reader itself? Because the reader has to be there sending power. I mean, and you're going to get the reading back. So in your example, there has to be a reader, right? Because otherwise, you can't even take continuous readings. Yes. Why not bring all those readings back and process them?
The communication channel is valuable. It's bandwidth limited. What's power and bandwidth limited? You know, these things run at kilobits a second, not megabits a second.
In the passive case, aren't all of the readers passively replying all of the time? I mean, how do you negotiate the channel right now?
Oh, so
Code
actually,
division
maybe
complex, right?
I didn't mention that, but here's one interesting thing about RFID technology. The reader sends out the signal. The backscatter happens at the same time. So unlike most wireless technology you're used to, where only one person is kind of transmitting at a time, if you like, the tag and the reader are transmitting at the same time. The tag is transmitting a power signal, usually without information, though it could send information. Sorry, the reader is sending the power signal, and the tag is replying at the same time. So those signals are all mixed up, and you actually have to, you know, a key job of the reader is to decouple those two different signals.
So it's by code division?
No, it's not by code division. It's literally two signals are superimposed at the same time, and the reader needs to subtract the signal it's sending. It needs to cancel the signal it's sending from the signal it's receiving to find out the tags.
If there are a dozen of these tags in the room, or if there are hundreds of these tags.
Yeah, and there's a multiple access protocol, which we'll get to eventually in about 20 slides, for how multiple tags contend for the channel. Yes, there's a multiple access problem here as well.
Even in the passive devices?
Yes, even in the passive devices.
Are the passive devices not so passive that they are not able to negotiate a multiple access protocol?
No, they are able to negotiate a multiple access protocol. It's a well-defined state machine that's in a little bit of silicon.
Gotcha.
So it's fixed function that's built in to allow them to contend for the channel. And Jitu, sure, you could come up with alternate designs, but just wait till you see some of the applications, and then maybe you can go through in your head and decide whether that would be a better design or not, and I would claim that the computation is useful. So we'll see. Okay, so let me just tell you a little bit about these devices. These are very cool devices. There's a WISP. You can see that they're small. This is a discrete device component just on printed circuit board. That's the WISP in the middle there. That would kind of shrink to just a small dot if this was an integrated circuit. All of the width there is the antenna. And it's on PCB just because it's easier to make them that way. Again, this could be folded in a different way and could become some little sticker the size of regular RFID. There's power harvesting circuitry on this board. Really, the reader is sending out a signal. The tag, just think of it as rectifying that signal. And then, using some of it to charge up a capacitor and store a little bit of energy. That is energy harvesting. And that sort of runs whenever there's a signal to control it. There's a microcontroller on this. It's an MSP 430 at the very low end of the family. And there are other things there too. I think there's about 8K of program space. There's up to 32K of flash. Now, these figures will all change over time, but it's just to give you a sense of what these things are. These are obviously much more impoverished than many of the sensor networks you might be used to playing with. There's backscatter communication, right, which is basically the tag just modulating the reflection coefficient of the antenna. And there are sensors. So what kinds of sensors? Things like 3D accelerometers. Everyone has to have a 3D accelerometer, whether you're a Wii controller, a hard drive, or whatever. So we're going to have a 3D accelerometer. They actually turn out to be very useful for all sorts of ubicomp and mobile computing scenarios. And we also have versions with light, temperature sensors, LEDs that you can actually flash for a bit of output, things like that too. You can make all of your own kinds of sensors. Audio, microphone. Yes, Jitu?
I've been wondering
I'm
ever
going to
since
give you
you
a
said
quota.
actuators.
You know that?
No, I've been wondering ever since you said actuators on the first slide, how are you going to get any actuator on this? And so LED is the only actuator you have, or do you have some other
Yes.
actuator?
It's really about sensing. It's mostly about sensing. Now, there could be other kinds of actuation and control, but the LED is the only example you're going to see here. We just found that to be more useful. Because there's not enough power to, whack you, right?
I was hoping for something.
Okay, so
Him too.
can't reach. Okay, you can also come up with some novel sensors. Just so we're not kind of constrained to accelerometers. Here's just a very quick example. Capacitive sensors can be used for all sorts of things, including touch. So this is a version of the WISP that actually has a touch sensor built into it. It's actually, the novelty here is that it's combined with the antenna, so you can use it both as a touch sensor and as an antenna at the same time. This is useful if you sort of imagine some of these things in scenarios where you want an object to do something if someone is touching it and holding it. Maybe you want a card to do something, do some transaction if someone's actually using it, but not if it's just in your back pocket in your wallet. It's almost two-factor. Okay, this is the WISP. I want to point out, this is actually a fairly mature platform for a discrete implementation. You can see we have been working on it for years. And these are just different models. Over time, they've gotten more capable, although I gave you the capabilities for the latest version. You can see it's really still quite small. But we've sort of gone from, in the time I've been there and involved, from Gen 1 to Gen 2 and changed some of the antennas so it's kind of more easier. And the devices have just got a little more capable as some of the low power components you can get have matured in the market. Okay, and eventually it would turn down to an integrated circuit, but you need a bit more money to make that happen. The good point here, maybe to stress, is just that these devices become more practical and get better over time. So here's just a little bit on scaling. This is what happens just for a regular WISP versus distance. The power you can get from a reader is going to drop off fairly sharply with distance, at least as fast as distance squared. Right? This is just freeze. And that's going to limit your operational range. Yes?
Wouldn't it be even faster than that? It's really electromagnetic coupling, so I would say it's DQ, isn't it? It's not RF, right? It's actually coupling for the power.
Well, in the far field, so this is not any of the inductive modes.
Oh, I'm sorry.
Right? So this is far field electric, and you're harvesting the signal. So I think it is D squared. But I mean, D squared is actually a little optimistic because there are other factors. But in any case, the power you can get sharply decreases with range, and eventually you hit the limit. So this limits operational range. If you need so much power, you can only get it so close to a reader. This graph, I'm sorry if you can't see all of the details, but basically it shows you as you get further away, approximate distance, equivalent distance in terms of power. If you get further away from the reader, the maximum voltage you can charge this little capacitor up to, so the energy you can harvest drops down, and the response rate, the number of queries from a reader that it can answer, drop down too, because it has less power. It can kind of run less of the time. And eventually we get down to a point where the platform needs about 2 volts to run. It needs to be able to charge and get that much voltage and charge things up. So the error rate skyrockets and things stop working here. Some of this data is a little old. The range is now about 4 meters. So we've got about 4 meters that these things will work from a reader, which is not bad, actually. What's more, over time, this gets better. On the right-hand side there, you basically have Moore's law. Or at least that's the curve underneath you can't read. We think of that as, wow, there's not a lot of resolution on this. It's much better on my screen. Yeah, Galen.
Your range?
I'm sorry?
How big is the transmitter is that? So your 4 meter range.
Given how big the reader is?
The transmitter?
Oh yeah, the transmitter, yeah.
Well, the power from the transmitter, you can go up to 4 watts.
Okay.
Okay, so this is quite a lot. So this is FCC limits. Right? And most readers that you'll see, send a watt or up to 4 watts. So they're already doing this. Yeah. So, I mean, this is a lot more than a wireless access point. Moore's law, everything's getting smaller, computers are getting faster. You all know that. But what's good for us is that this means that the energy, Moore's law helps with energy efficiency too. You need less energy to run these smaller things. That means effectively the energy, the nanojoules per instruction is going down over time. So for a fixed workload, right, so we can either run bigger workloads over time or we can run the same workload further out. If Moore's law, if we're doubling every 2 years, this means that our range is doubling every 4 years for a fixed workload. Yeah, did you have a question?
Yeah. So what's the programming model look like if,
so basically these things are getting powered by an external device, and you can always be moving this device around, and the sensors maybe, that program on the sensor may be coming up, maybe coming down. I mean, what does that look like? I mean, you have to reason about things like the restartability of the state machine that's on the node.
Sure, so those are some of the systems and networking challenges. I'll get to some of that and tell you a little bit about an energy-aware scheduler that runs tasks on these, just briefly, only a few slides. But we are a long way from sort of reasoning about the programs on this space. It's just, it actually takes a lot of effort just to get small programs to run on this platform. There's a lot more that could be done and that we're sort of starting to do in terms of just the architectures for programming these things, what the programming models are. But so far we've really just been driven by the technology and prototyping applications and the very first issues we run into, which are energy, just how do you deal with the fact that energy is whatever, and some of the networking protocols. We've done that rather than programming models. Yeah?
So, if I remember correctly, different components require different voltage to run. A microcontroller may be more resistance to lower voltage than the flash memory. Some sensors probably fail the first if the voltage dropped below a certain value. Have a look at that and sort of trade off what to put on the board, what not to, and some of the programming challenges?
The short answer is yes. I mean, you're right. So for instance, we need a higher voltage to write to flash. So by the time you're about to black out, you've already lost your ability to write to flash. So you just need not to get there in the first place. We have looked at that. It's not like there's a final answer though. This platform is evolving all of the time. So right now we're trying to produce the WISP version 5. We're actually going to take some of the communications done by the microcontroller. We're going to move it down to a CPLD if we can. That'll make a huge difference to the platform. There are all sorts of things like this. So you should really think of this platform as as evolving due to considerations like that, of that kind. But there are at least half a dozen sort of things there. These things are really not done. This is a brave new world in a pretty wide open space. So please don't think of any of this as like completely baked or done. Okay, so Moore's law, things get better over time. We can run things further out. This means that, over time you'd expect it to be more practical to put computation in all of these different systems, in all of these different objects, and run programs over everyday objects. I told you about the tag. It's also a reader. You've got to have something to talk to these tags. So we've also prototyped a reader. This is a very flexible reader here. You can see it's based on software-defined radio techniques. You can see here just a PC and a USRP. And this is sort of the output. You can actually see here reader commands and tag backscatter. That's a trace taken from a real interaction by that reader. I guess it's a fairly standard sort of software-defined radio challenge to implement this. The channels are fairly narrow and the data rates are fairly small, so there's actually not a lot of difficulty in terms of handling the raw samples to run this on a low-end SDR platform. As usual, some of the challenges are latency, right? Being able to turn things around quickly. You've got like 500, up to 500 microseconds to turn around between receive and the next transmission. So that's a little tricky in just some of these platforms. And more so than that, there's also the signaling issue, the fact that you're transmitting and receiving an issue at one time. That's kind of fairly unique to RFID, and that's the sort of thing that requires just a little bit of engineering. We were happy enough when we separated a transmit and receive antenna by about that much that we had enough sort of SNR headroom to do that cancellation and be able to receive the signals. So our reader does not have the range of commercial readers, but it's still fairly good. It'll go out to a few meters. Because it's a software-defined radio, it enables us really to change protocols at a very low level. We can define our own physical layer and MAC layer protocols. The EPC Gen 2 protocol, the standard for RFID, think of that as the starting point. We really use that as a point of departure and look at the problems there and look at how we can change that. But all of these protocols we're going to use will have the features that they are RFID style, with the reader powering things and the tags using backscatter communication. That's really a hallmark of this situation. By the way, there are all sorts of paper references. I invite you to sort of follow up. As well as having a WISP and a reader, we've also tried to provide a lot of EPC Gen 2 compatibility. And the reason for this is it helps us a lot with deployments. Right? We can sort of ride the wave of commercial RFID readers and tags that are out there. So the WISP in particular can be powered by and communicate with commercial UHF RFID readers. We like impinge readers, actually. Right? Now, to get sensor data to and from the tag, you're going to have to do something. The RFID reader doesn't understand that, so you have to encode it in some way, either in the identifiers or by reading and writing memory on the tag using high-level commands and building something on top of it. Similarly, this WISP reader, since we've implemented EPC Gen 2 on it, we can talk not only to WISP, but to commercial tags as well. So we have all of these sort of different interactions possible. So it allows us to have mixes of deployments, as well as kind of experiment with brave new world protocols sort of thing. Okay.
How big is the reader? Like when you show it on that picture, how the white box?
Oh,
Yeah.
they're like that big, that tall. It's just it's antenna design. It's whatever antennas you want to use. You can use something else that'd be smaller. Yeah, there are many RFID readers that sort of are in smaller packages. It just depends, where they are. Some are sort of ceiling mounted and smaller. Okay, so I've told you about the technology essentially, that it exists and something about, what it is. I'd like to just switch gears a little bit and just talk quickly about applications, since if there's nothing we can use it for, this is a little bit of a waste of your time. Fortunately, there are some things we can use it for. Okay? And really, you could think of all of these as instrumenting the physical world in different ways for different ubiquitous computing scenarios or cyber physical systems. They sort of leverage the wireless and long-lived nature to be able to install these things in locations that you just don't need to get to for a long time, or which are otherwise inaccessible. Think of this as infrastructure without wires because you've got these tags. And many of them also will leverage the fact that because tags are small and inexpensive, you can deploy these fairly widely. And I claim that all of the applications that follow are the sorts of things which should be hard to do with either RFID alone or sensor networks alone. I'm not going to claim that they are the best applications in the world. They're just different kind of UbiComp scenarios. Maybe you can improve on them, in which case I would love to talk with you. Okay, so here's one we've fooled around with a little bit. Cold chain monitoring. Supply chain monitoring is a main motivator for RFID. And one scenario that many people have talked about is going beyond that and monitoring the status, not only objects, but their status as they move around the world. So, here we've used cartons of milk, and we have a WISP there that's instrumented to be able to sense the temperature of the milk and how full it is using a capacitive sensor. But a better analogy might be, a better object to imagine here might be a bag of blood or something like that. Objects which are, have some value and they have some requirements in how they're handled. You just don't want to leave them out of the fridge on the counter for too long. It's not a good thing, right? With the kind of systems we're building, you can imagine that these, a bag of blood is labeled with just a small little WISP sticker, which can sense things like temperature and so forth. You can then set up a system whereby you're near the reader, you're in the proximity of the reader and powered when you're in most of your time. You're sitting in the fridge, everything's good, that's exactly where you should be. When you're in transit, though, you're out of the fridge, this is when bad things can happen. What we can do is use programs running on the WISP and sensors to be able to record the experience, what happens to this. This would require then running for a little while away from the reader. So this is the example which actually we stuck a super cap on there. It has disadvantages as well as advantages. You actually have to power it for a long time before this thing gets going. But you can do things like this and monitor the vital statistics of objects while they're in transit. Yes?
So when you say that the sensors need to be able to run for a brief period of time between the scans, how long are you thinking that brief period is going to be? Because if the capacitor is really that small, it seems like you really need to...
So does it take you to drink milk?
That's neither here nor there. My milk addiction is a thing of the past. That was in the 80s. I'm not on trial here.
Okay, so that's a great question. And in fact, this application is the odd one out. In that most of the WISPs we use, they will die within seconds if the reader is not on. And for many objects, you only need to do things when the reader is on there and saying, do something. In this case, we stuck a super cap on it. It's substantially larger. Actually, it would last for like half a day, right? And so that was ample to kind of record what happened, for the milk, to the milk.
Why do you need to know for the milk? What matters is the temperature is when you got it back and how long it's been gone for the fridge, both of which you should be able to extrapolate the first time it gets in.
No. Well, for a lot of things like a bag of blood, you really want to know what that thing experienced. Just knowing the temperature of the fridge and, how long, it's often in transit from one place to another. So the sensing is done like on the whatever, wherever it goes. And you don't Maybe in some settings you would be able to infer it from other data, but the safest thing you would have is actually on that object. This is one fridge to another, and you can also imagine with a bag of blood, you basically encode what it is and other restrictions, and be able to check all of these things automatically. Okay, Stefan.
How long does it take to recharge?
Well, that's actually the problem with this one. So right now it's difficult if you add more storage. It takes a long time to recharge. It takes an hour to recharge, I think. Right?
Wouldn't it be hard to put a coin cell battery on it?
No, you could do that. You could look at all sorts of other designs which have batteries. Yeah, and we have chosen sort of not to do that. Just to sort of say, well, we're going to look at really RFID-like stickers, which are ultimately disposable on some objects if you like. As soon as you go to coin cell batteries and all of that, I think you're upping it. At some point, though, it begs the question of what's energy storage. If we have a capacitor that's so big, it's some kind of energy storage. So I sort of imagine that some of the sensor networks and enhanced RFID worlds may eventually collide. Rather than a coin cell battery, you might have a trickle charged battery, which you could wirelessly recharge. That would be great. Those things aren't viable now through many charge and recharge cycles and so forth. So we're back to exactly where I showed you with capacitors. So you could try all of these other designs, and they all have pros and cons. It's actually not my intent to convince you that this is the design, because this is a work in progress. It really is my intent to convince you that this is an interesting space for you to be thinking about. I mean, these are small computers, on your coffee cup. Maybe not on your coffee cup, but on, all sorts of objects around the world. We'll find out find out how much milk you drink by looking at your coffee cup, right?
So one of the things I find interesting is, I think one of the trends is to not think of this as sticky notes or sticky things. They're actually built into the carton itself. So when you buy it, it sort of already has the RFID in it. So you don't have this thing about sticking this or battery.
Right, so you don't have to. You're absolutely right. Thank you. I should have mentioned things like that because, we really sort of imagine that some of these things could be built into objects. Actually, you can even build them into electronic objects. Imagine like a cordless power drill or something like that. You can, maybe it's logging a lot of statistics of when it's used and what's going on and what state it's in or whatever. If you actually have a little RFID, something in here, enhanced RFID with this style of technology, you can communicate with it with a reader, when all of these drills or other things are completely off and not powered or not doing anything. Right? So this could be a new capability built into all sorts of things, in addition to whatever other interfaces they have. Okay, that's one. Here's another one. Activity detection. In fact, there are many different applications people are looking at for these things around activity detection. The idea here is that you instrument everyday objects, and by looking at traces of what objects are used, you can recognize what daily activities are happening. A prime scenario here that's come up that we have explored, and this is like a mock apartment sort of thing, is elder care, actually. So this is, by providing technology like this, you can kind of recognize what's going on, whether people are, using cups and kettles and making tea, whether they're eating and drinking or exercising or getting out or just sitting on the couch watching TV and so forth. This is actually very useful for elder care in the sense of helping elderly people to stay in their homes for longer. I mean, healthcare, as you all know, is something that's billion-dollar industry. It's incredibly expensive, right? So a little bit of automated support like this can actually be advantageous to some people. And you can imagine activity detection in many different settings. This is actually quite, and so the data here is just, we actually compared our system, where you're just recognizing what's going on from the objects, to another system, an earlier system where you had to essentially tag people with a bracelet and a UHF RFID reader to work out what objects they were near. It's more convenient not to have to instrument people at all. People don't really like being instrumented, right? And you can see we actually have accuracy that's pretty good compared to this other system. This earlier system with the eye bracelet there, we have the reader, was actually tested in an elder care facility. So a lot of these things are quite real and will roll out to products sooner or later. Okay, robotics. We haven't really done anything in this space yet, but I think it's right. Robotic navigation is sort of happening or happened. And these days people are moving on to robotic manipulation, right? Recognizing what's going on with perception and then being able to manipulate the world with robots. It's hard. Vision is sometimes fragile. And so what's likely to happen is you're going to use many kinds of sensors, whatever you have available. This kind of RFID is another one, which could be used in many different ways. RFID with a little bit of sensing, if it's slapped on objects. You would know what objects are roughly in the vicinity before you can perceive them with other sensors. You can localize them in ways, not necessarily just signal strength. Actually, it turns out that the phase information at different frequencies is quite useful for getting a bead on what's where. If you imagine accelerometers in objects, they can actually help you determine the pose, right? Because you have acceleration with respect to gravity, even for an object that's not moving. You can often gain some information about, which way around or up it is. That's actually very useful for, computer vision and everything else. When you have an object, the acceleration, if it's moving with your whatever, your manipulator will tell you whether you have a good grasp or not. Capacitive sensing is useful for contact events, so you can tell that you actually just touched it and you've got it. Now is the right time to do it. These may sound small, but they're all very hard problems in robotics to address, actually. So we think this has some potential. And we'd like to explore it in the future. And of course, you can also have attributes, on an object and a tag. Maybe have a model of what it looks like that you can just read and then know the 3D models of objects in the room to help you with your perception. Okay, and here's something completely different. This is not my work, actually. This is work by other people more so on the E side of UW. These kinds of RFID with sensing seem to be quite useful for non-intrusive physiological sensing. So many people, or a rather large number of people, have devices like pacemakers, insulin pumps, and so forth. All of these sort of things that are in our bodies. I've never tried it, but I imagine it's not fun getting your pacemaker battery changed. This is not a good thing, right? Here you have sort of devices that don't have any batteries, that could be wirelessly recharged and so forth. Maybe you would need something around on your body to be able to charge it, but it's an interesting alternative to explore. Here's some work in that vein. This is like a little neural preamp. So this is like to implant in a moth to be able to record what it's doing. Right? And there's the moth, and actually there's a big wire coming from it to a WISP. This is Brian Otis in EE, and they actually went further and they kind of came up with an IC for some bits of the WISP. They put it there, and here's the moth flying, right? And it has, something clumped onto it, so you can get record its neural activity. You can actually see when it's flapping its wings. What you can't see in that picture is there are actually wires coming off it to kind of go elsewhere to get some of the data out. It didn't all quite fit on it, and the moth doesn't fly quite right? Okay, but it's still pretty impressive that they could do it. The world is changing around us, whether we like it or not. Okay, and there are other applications. One thing many people have been interested to use these for is security. In fact, there have been lots of work on RFID security protocols, most of it on paper. Because where are you going to get a programmable RFID tag to try any of these things out? Well, here, that's where. There's also other work. Someone's used it for undersea data collection. Again, this is a problem of getting across a barrier. You have these glass spheres that go underwater, right? And you really want to send information from one side to the other, from where you're sensing it to outside to the electronics. But you can't drill a hole through the glass thing that sort of has various reliability and cost issues. So we'll wirelessly send the data. And other people have used it for different kinds of activity detection, sleep monitoring and so forth. Okay. Now I feel I've given you a sense. So now I feel we've talked a bit about the technology. I hope you know a little bit about it. We've talked about the applications a bit. I want to go through fairly quickly, I realize I don't have that much time, just some of the systems and networking issues around it that I think are fun to look at. And I'm going to talk about two of them. Really, energy is where we've done something. And the networking protocols really is where I'll mostly tell you about the opportunities and things that we would like to do, having looked at the issues a little bit. Well, here are the two big issues that come up. I mean, the number one is just energy. Power and energy is just very scarce in this environment. The applications you would write are power limited in terms of what they can do, their functionality, and in terms of the range, how far out they can actually run and do things. Right? And there's little energy available just because of this drop-off. So whatever energy you get, you better use it well. The question here, the key question is how you run a range of programs when you have this low and intermittent source of power. And in the networking side, the key question really is how you design protocols that let WISPs send rich data, messages and rich data, as they need to stream sensor data. It's a very different workload than RFID. And it's a very strange setting. It's very asymmetric compared to 802.11 or most settings we've looked at. Right? That's because the readers are really powering these WISPs. They're in complete control of when the WISPs are on, modulo a small wind down period. Not only that, but the WISPs themselves, they can hear and communicate with the reader, but they can't hear one another, and they can't directly communicate with one another. So it's quite an asymmetric setting. So I'll just present just a small number of slides, a few slides on each of these areas to tell you what we're doing. Starting with energy. Okay, so on the energy side, the goal is to use the energy you can get well. That sounds really obvious. What exactly does it mean? Well, recall that the power you can get, the maximum power you could harvest, is going to fall at least as fast as d squared. Okay, so here it is falling off. Just, this is at 900 megahertz, assuming 4 watts transmission, and you can see that we're getting, milliwatts, or, maybe hundreds of microwatts, or less as you go out further. So that's all the power that's available. Excuse me. If you have a task, a small task that you want to run, the rate at which you can run that task is going to fall off, according to that graph, as you have less power available. But ideally, it should fall off no faster. That is, you want to be able to run any task out to your maximum range. Maybe it will execute less frequently and be able to sample things less frequently, but you want to be able to run all programs in whatever situation you find yourself. That's what we're shooting for. To do this, you need to be able to balance the available power you get from the reader with the consumed power that goes out, because there is very little in the way of buffer here. And it turns out there are many costs of buffering. I'll get to just a little bit. That balancing act is surprisingly difficult, actually. Why would that be? Well, because there's a lot of variability. The input power you get varies a lot with the distance. You can see that graph. It also varies with the reader frequency due to multipath fading. And the reader hops at least every 400 milliseconds around. So you can have variations of order of magnitude in the power you're getting over time. Right? That's quite a lot to deal with. The amount of power you need, or output here, also varies a lot. It varies with the task. You may be doing, just gathering a sensor thing and checking to see whether you should be doing something. You may be running a protocol which does a little bit of crypto or activity detection on the sensors you have to decide whether a tag has followed a certain pattern or not. You could do all of this on the tag if you could run a program like that. There's also non-determinism here and a bit of variability, not only from the inputs to the program via the sensor data, but because of the wireless protocols. Right? There can be contention on the wireless channel. You may need to send more messages to finish your task. Okay? So these factors vary a lot. And what we find here is that the RFID model, the classic EPC model for protocols, doesn't work very well in our setting. The model there is just basically run whenever there's power. If there's any power, just turn on and run. That works for very simple programs which have a low worst case power consumption, because they'll be able to run that program out to max range and it will look roughly the same. Here, we're not in that case, in that situation. So we're going to need to adapt. What do we do? Well, first let me tell you a little bit about the WISP power model. Here's how it works. So we said that you already know that there's limited onboard energy storage. This capacitor is much smaller than a battery, actually by like about 8 orders of magnitude compared to a couple of AA cells. The tag will harvest power whenever you're in the proximity of the reader. How much power you get is going to vary, but the circuitry there will basically harvest whatever is around. And then, so this will go into the energy buffer. You've got a little bit of a store. And as you run, you sense, compute, or communicate, you expend energy fairly rapidly. Right? Actually more rapidly generally than you can gain it. This means that it's quite normal to exhaust power every second or even many times a second. Right? It's very different than a sensor network scenario where your goal is to maximize the lifetime of the sensor network measured over days or months or longer. Here we're talking about seconds. And you can see here, this graph just shows the green is the WISP voltage. That's the energy, proxy for energy. It's going up over time and jumping down fairly sharply whenever the WISP actually turns on and runs any program and does anything. There's some reader activity messages. However, to a first approximation, they are not affecting whether you're getting energy or not, because the reader is sending a signal, whether or not it's actually sending commands, and you're getting energy in both cases. So here's our solution, instead of RFID scheduling, to be able to run programs on WISPs. We have built an energy-aware runtime called UDrop. I only have time just to sketch it to you very briefly. I'd be happy to talk to you more about it later, and some of you may be going to NSTI, so there's a paper on this next week. Now you'll be primed for the paper, and you can ask Michael really hard questions, right? So the job of UDrop really is to adapt how programs are run to the RF power that's available and the size of the task. Instead of simply proceeding with an RFID model where you just try and run things, whenever you reach a minimum turn-on voltage. So Dewdrop is really trying to ask whether there is likely enough energy to run a particular program. The only decision it has to make here really is how long to wait and continue to harvest power before starting to run a minimal task which can't be interrupted. You can imagine a big task broken into all sorts of little pieces, but at some level there's some small unit that you just want to get done. Right? How long do you wait before you do that? If you just turn on and try and run at any time when the input power is really low and your task is going to take more than available, your task will fail. And that will mean you've just completely wasted all of that energy. Right? Because it didn't complete, you didn't get the result, whatever. While it's not so obvious why, there are also penalties for waiting too long. We sort of discovered this from looking at platforms. This is due to nonlinearities in real platforms. It costs more to gather energy. As you fill up a capacitor, as it gets higher, it costs more and more to gather it. There's also different kinds of leakage, and there are other nonlinearities in the platform. This was sort of a little bit of a surprise to us because we naively sort of imagined a bucket of energy and you just fill it up and you can use it for whatever you like, and as long as your bucket's full, it's okay. This is not really the case, I think, in any real platform because of the nonlinearities. Some of that energy costs you more or less than some of the rest of that energy. And in general, you just sort of want to have enough energy just to run what you want to do and collect no more. Trying to collect and storing energy is just not that efficient in these systems. Dewdrop works by balancing these costs. It's actually reasonably difficult to do, to implement on a small system. Yeah?
Sounds like the model you're considering has two states. One is where there's no energy and you're off, and one is where you're running instructions and you're running a program and you're on. Have you considered anything in between those two, like say keeping memory alive but not executing code as a low power state? Would any of that change the modeling?
I'm not sure how much it would change it. Actually, I've skipped that state, so we actually do have a sleep state in the middle where memory is being maintained.
Okay.
Right? So but you're trying to get through something before you kind of hit that state. So we do have that sleep state as well as active, as well as completely off, cold start. The goal is really to stay in the sleep and the active states. And you're really duty cycling the active state depending on how the energy is coming in and what your task is and just trying to make it work. That's what you're really trying to do. It's actually, it sounds fairly simple. Hey, let's just duty cycle it. It actually turns out to be fairly hard to do in practice, partly because this is just such an energy-constrained environment. Just asking the question, hey, how much energy do we have? Burns a lot of energy and a lot of time. So you don't really want to do that. Okay, so, and especially the charge times here before we kind of get going on a task range from, milliseconds, well, tens of milliseconds, to tens of seconds. So it's a very large interval. Any kind of fixed thing that works for one end, is going to completely screw up the other end. So we sort of use adaptive strategies here, as you would expect, different kinds of exponential backup and so forth. And very careful instrumentation, because you can't, we're only trying to indirectly infer where we are in terms of a balance point by looking at cues for how often it looks like it's too early and too late, and we're just assigning costs to these. But if you do this, if you track these things, and if you try and balance a little bit, and if you're careful to make sure that your energy scheduler really doesn't consume very much energy, you can get a substantial win. Here's like just the tag response rate for two different tasks, the blue and the red line. The blue line is just, a lightweight task, just sensing something, getting a data sample. It goes down, d squared. The red line is the same line when Dewdrop's on. It's the same kind of line. That's great. That's actually what we want. It's just at a lower place because it was a more heavyweight task. It involved some transmission and so forth. So you could do fewer of them with the available energy. What happens without Dewdrop is that with Dewdrop you can run this task out to pretty much the full range. You can run it out to 3.5 meters. Without it, basically, before with our default hardware scheduler where you just do something that's more analogous to RFID, you just stop working when you hit 1.5 meters, right? So we have succeeded here in being able to run across a range of different programs and a range of distances and so forth, be able to run some programs at least. This also helps in terms of some application scenarios. This bottom graph is taken from that picture of the apartment. Slightly different setup, but a different apartment where we're looking at coverage. How many different tags can run a task, given one reader somewhere? And the answer is that when you use this scheduler, you basically improve the coverage a lot. Because while there were some tags which were just fine, doing any old thing, Other tags were in a place where they really benefited from their scheduler. And so you get either an increase in coverage or you can reduce the power you need for a given coverage. Yeah?
Be stationary, or they something
No, they
predict their mobility?
we don't predict their mobility. They could move around. I think we're assuming that things like motion is happening, is changing the situation relatively slowly, such that you can adapt to it. And that will hold for, in the apartment scenario, that's generally fine. Maybe that won't work for some other situations, but it's okay for what we looked at. Yeah?
So how many scenarios do you think you got a fixed reader, like in the apartment, the reader is just embedded in the ceiling? Will your power problems go away because you basically have an infinite power budget? And is that, or where do you see the transition between reader and
No, I don't think the power problems ever go away. And the reason is, even if you've got a reader in the ceiling, it's just blasting power all the time. The amount of power you have when you're close to the reader is like 10 times as much as the amount of power you have if you're over in the corner. You could either write all your apps to just assume they're at max range, in which case you get apps that just can't do very much or run very slowly. Or you could write your apps to run, with lots of power, in which case they would just die in the corner. So what we're really trying to do is make it so you don't have to do any of that. The system will adapt. It'll take your task. It'll run it as much as is humanly possible, right? And there are, besides just that, there are other factors which cause variation too. So you want to be able to adapt to them. Okay, that's mostly energy scheduling. Let me just say, we are looking at some other things. There are some complementary strategies here. I talked about breaking things into stages, checkpointing things in different way. You could even use non-volatile memory, sending things to readers. These are all interesting things to look at, but we've sort of gone for the problem that was troubling us the most at the moment. You could do all sorts of other things here, actually, that'd be interesting. You could even coordinate with readers. There's no reason they sort of need to turn off just when you I just needed, a few more microwatts or milliwatts to do something. Reader stopped. You could change that if you wanted to write new protocols. I would not claim that this is like the most important thing on the list, and that's why we haven't explored it yet. What we did find out actually is that some of this power debugging work is actually very hard. What goes on in all of these WISPs just before they die? Well, who knows? You can't see. I mean, it's not like it has any power to tell you anything or send a message. And so, in fact, for quite a while, it took us a little while to develop power debugging tools, essentially. And here's a debug board that's powered yet does not influence the behavior of the WISP. And this sort of allowed us to see various interactions across WISPs. As you have more and more WISPs, due to the wireless protocol and contention, their energy consumption is changing. And we can also see that current RFID protocols are actually somewhat demanding, because when you begin to participate in one, you need to go through a whole round to kind of keep synchronization with all of the messages to know when you need to send. So all of the tags are sort of burning more energy than they would need to. It's fine for RFID if you've just locked it to that out in the extreme, but in this world it's not necessarily a good protocol. Okay, so I'm basically jumping ahead to protocols. And here I really just want to tell you about some of the opportunities, and I just have a few slides left. So hopefully we won't all be here to 6, okay? So I think there are a lot of opportunities with some of these networking protocols. It's a very different setting than 802.11, so let me just tell you a little bit about it. Here's how the EPC Gen 2 communication protocol works. It's based on slotted aloha. See? All those randomized protocols you learned in your networking courses long ago, they are useful, okay? Right? Yeah, Stefan was expecting that, yeah. It's slotted aloha because the tags can't hear one another. So when they talk, they may collide. Slotted aloha is a protocol that really predates Ethernet, right? It's, even, it makes even weaker assumptions about who can do what things. So it works something like as follows. Okay, so the reader is in control because it's sending the power that's letting everyone do everything. So it sets the timing and the power. It issues the slots in slotted aloha. Slotted aloha is a randomized contention protocol. Each tag is going to pick a random number of slots to wait and then backscatter its response in a random slot. If other tags pick that slot, it may collide and then you have to go through some dance. So you can see here, the reader is sending out query and query repeat. These are the slots. This tag has chosen to wait and respond in the third slot. It actually responds with a little handle, a 16-bit random number. And if the reader acts that, it then sends the whole identifier. Why does it do that? This is just smaller if there are collisions, so you're kind of balancing the costs of different things. And at this point, the reader can now interact with the tag and ask it, hey, what's going on, and get a little bit of data or store a little bit of data. This is called singulation to get down to a particular tag. From our point of view, though, it has some shortcomings for writing WISP apps. It's really optimized for identifying an unknown set of tags. Okay, you go through this dance to identify all of the tags before you can actually talk to them and issue any commands. Now you then have to work out where to put the sensor data. There is no place for it. We can overload it on identifiers, or use memory read commands and pretend it's part of memory. But basically, it's a poor fit for streaming sensor data from a slowly changing set of nodes, set of tags. You really just want to stream the sensor data, but you have to go through this dance all of the time. A second sort of defect is that the reader is logically in control. Because it's for an inventory application, it's just seeing what tags are around. It starts all chain exchanges and it goes through this identification process. This means that WISPs can't easily, in any of the current protocols, initiate their own messages or talk to other WISPs in the vicinity. So there's no sort of, you can't easily have one WISP ping another WISP, or send a message or receive a message or anything like that. The protocols just don't work that way. There's no narrow waist, if you like, on which to build higher layer applications. So we're looking at both of these areas to explore them, because I think they would both be interesting. You can imagine streaming sensor data much more effectively by assuming that you have roughly the same set of tags around, and they're simply changing the values, the sensor values over time. So now you've got to make the protocol work, because the set of tags will change slowly over time, and there are all sorts of things you need to be careful about. But basically we're looking at reusing some of the short identifiers as handles and treating them as addresses, and in this way you can stream sensor data much more effectively. We have some prototypes that give you up to 5x improvement, simply because you're not using all of the rest of the channel on all of this dance. And this is the sort of thing you might even be able to approximate within the Gen 2 standard. We're also looking to integrate WISPs with IP via a reader, so that you can, from your computer ping a particular WISP, or it can ping you, or it can send you a message when it arrives somewhere else. This is really thinking of the readers not so much as part of an inventory application, but an AP, right? That are simply there to help WISPs operate in the same way that APs just help your laptop. So think of the reader there as providing power, internet connectivity that you need, and even delay-tolerant networking services. Since some of these WISPs will often be off or in different places and so forth, you can kind of rendezvous via the reader. This is really an architectural change of viewpoint that we're sort of exploring, that will let WISPs initiate all of these data transfers, as well as naturally fit with WISPs which run different apps in the same room. And that's just kind of, there's no rocket science there, but it's just fundamentally different than the way you think about inventory apps and how they work. Okay, I'm a little conscious of the time. And that's all I had for you on the systems and networking protocols. Hopefully that gives you a sense of some of the issues there and some of the interesting things to play around with. I just have a couple of slides on the community. We have been building this WISP community, actually. So both this WISP tag and the reader that I've talked about are freely available to the research community. There's open source hardware, and hardware designs, at least, and software up there that you can grab. These are the only platforms that we know of this kind, that are programmable RFID or RFID readers, where you can really mess with at a very low level, that are readily available. The SDR reader is also actually a monitor, so you can use it as an RFID monitor. If you're looking at any of these systems, the thing you'd want to know is what's going on at a low level. But some of these monitors are incredibly expensive, whereas you can just get a $1,500 USRP and attach it to a PC and see what's going on. Here's, you can look, there's much more detail and all sorts of pubs and things off this URL if you'd like to look. We've also sort of been to build a community trying to encourage others to write applications and experiment by themselves. We ran a WISP summit concurrent with Census, or co-located with Census 2009. And we also issued a WISP challenge, a request for proposals for other groups to say that they would like WISPs, that they would be interested in doing things with them. All of these efforts have been quite successful, actually, and we're very pleased that there are now WISP starter kits, 36 different research groups. There's a sampling of them there, and more importantly for us, there's now sort of a stream of pubs. Some of these are our pubs, not all of these are our pubs. Other people are starting to use WISPs and publish them and do some work there, with work spread over security as well as system stuff, and some applications, although not as much as we'd really like to see. So, in conclusion, I've talked to you today a little about some RFID technology, which I hope we'll see a little bit more of in the future. Really, I'm not going to go through all of this. I just hope that you've heard something that would be interesting, and then you can sort of imagine some of these small computational systems as part of the everyday environment, and that would be an interesting area to look at. And I'm happy to talk a lot more about this, or about all sorts of other kinds of systems and networking I do. Thank you. I'll take some questions.
You said that you would provide a characterization of applications where you can't use reader as the computing, and this simply send the reader flags. I'm just wondering, do you have like a crisp characterization where the WISPs need to have computation apart from maybe whatever little bit is needed, just read the sensors and back? You said network bandwidth might be a challenge, but I mean, what sort of application? I'm just trying to think of an application scenario where there has to be computation on these end nodes, and computation can't just be integrated on the readers.
Well, I wonder if it is simply a matter of performance, right? It could simply be a matter of performance. If you've got all of the sensor data and you have enough power to send it to the reader and run whatever you were going to run there. Now, I don't think that's likely to perform nearly as well in some cases. So some things that you could imagine doing are, activity detection, right? You have a stream of sensors locally. You're trying to work out if an object is actually doing something you care about, if it matches a target filter. You're doing that recognition locally. You're only talking and telling people about it, telling the reader on apps out there on the web about it, if it meets that condition. The alternative you're suggesting is you can just send all of that sensor data back, all of the time, and process it elsewhere. You could do that. That's a different architecture. It's a valid architecture. I'd be kind of surprised if you didn't run into a lot of bottlenecks in doing that on the wireless channel when you have many different tags around. And in addition, well, I mean, it's a trade-off. I'm not sure why you're looking puzzled.
No, but I mean, it would be a lot cheaper, right? I mean, the tags would be enormously more cheaper.
No, I don't think it would be much cheaper at all. I mean, really, it's just a tiny bit of silicon. That's not where the expense is. Well, I don't think it would be substantially cheaper. The other thing I was going to say though is it's hard to know ahead of time exactly what functionality you want on a tag. Witness all of the RFID security stuff. So maybe you put some scheme in there, and it's hard baked in, and all they can do is send the sensor data back. I guarantee you, as soon as you do that, someone's going to want to change what's on that tag, right? They're going to want it to do something else. And that's what a lot of the security community are doing. Is they're basically running little crypto programs and testing designs on some of these tags. I mean, that's using the computation for another purpose. It may be a while before we get to applications which really, you couldn't sort of imagine doing a slightly different way, because this is just the beginning. Yeah, okay.
Around density.
Density?
Yeah, how many of these tags how many tags can I put in this room?
So we've really gone up to 10s. 10, 20, 30. That's about it. And we can see interactions across tags because they're all contending for the channel.
Yeah.
And the amount of time to run a task gets bigger. Yes. Well, so, yes. Yeah. I agree. I mean, there are a lot of things that would be fun to do here. Doing anything with WISPs, unfortunately, it still takes a while to get going. It's fairly hard to. They're still fairly hard to work with. I think I think it would be interesting to see how they scale. Right now, I don't think that they would scale very well as you go beyond 10 or 20 or whatever, and that's because the amount of energy to run a task, because we sort of do the communication protocol and we're running for that time. It's growing with contention. And I think the challenge there is to ask, well, maybe that just means all of the network protocols are broken. Could we design different protocols, excuse me, that in fact would not work that way and would let us scale much more effectively? Maybe they're not going to be perfect, but we should be able to go a lot further than we have. I think that'd be an interesting area. We just haven't done it.
I guess the other question I have is in terms of, I realize it's a graph, it's not a simple answer, but how many cycles of computation do I get?
It varies with the design of these things. Thousands. You can have thousands of cycles. That may not make it, yes. you know, it's changing over time.
I guess one of the other things, so it's kind of hard to do a lot with thousands of cycles.
No, well, but on a charge. So, I mean, you can do more over time, right?
Per charge, right? That's a really interesting question. I guess the other thing I wonder is it CPU really the right thing to put on it?
Versus?
I don't know, maybe an FPGA, maybe, I guess kind of going back, because you just think of fixed circuitry, or, maybe by the time these things are commercially viable, we think about how you're going to program the hardware actually as gates as opposed to cycles.
Maybe. I wouldn't rule that out because, as I say, we're early on the technology. I think it all depends on the applications.
One assertion I'm going to make is that once you put a tag on something, you're not going to go reprogram it.
You're based on the sensor network world?
Well,
so,
yeah, I mean, in thousands of cycles, I don't know.
yeah. We would like to believe...
Yeah, exactly.
Yes, that's with the current hardware. That could go up orders of magnitude as things are scaled down.
The way you look at CPU here is not as a CPU. It's just a sequential operation versus a parallel operation. But if anything, that's better be done in a sequential way. Microcontroller is the cheapest to do.
Parallel will never get you lower power, does it?
No, I don't think microcontroller in this system is going to be the first one that fails. It's the sensor is going to die way before that. Like accelerometer needs a lot more higher voltage to run
That's true.
than the microcontroller.
So how do you divide the numbers that you put up there? You said that the power input to this thing looked like, at your range, was hundreds of microwatts. And that other graph you had showed like 100.
Yeah, up to milliwatts.
It's up to milliwatts, but at the low end of it, it's hundreds of microwatts. And on this other completely unrelated graph, you said that the energy per cycle is something like 100 picojoules per cycle. So if I divided correctly, that would say that if all of your power was going to the processor, which of course it's not, you'd get about a megahertz at maximum range. Right? That's million cycles per second, right?
Okay. Well, I haven't reconciled the data. I mean, the data from Moore's law comes from a completely different data set of processes.
But it makes you think that you can actually get
that
pretty
much should be
significant
available.
computation.
I mean, that's well beyond.
Well, I mean, that's not kind of for running the memory or the radio or anything else. But
I mean, over time, these things are just going to become more viable in terms of what applications you can. Okay, Stephanie.
How do I distinguish from one sensor from another?
What do you mean?
How do I know which WISP I'm talking to?
Oh, no! I knew we forgot something.
You can do it with barcode.
Come on, guys! Don't be such skeptics. So they have an identifier, of course, like RFID does, as well as sensors. And so when you begin talking in a protocol exchange, you may not know that you're talking to a particular one. You have to find that out during the protocol exchange.
And those are sort of done at fabrication time, or they can
Vision?
No, they can be reprogrammed.
They can be reprogrammed.
Yes. I think you can even in commercial RFID tags. Well, actually, you can't program. Yeah. Yeah. Yes.
Way cheaper to print electronics, so it cannot be reprogrammed because simply the technology becomes totally cheaper technology. Okay, so I wouldn't assume you can.
Right, all of the cost and business considerations would really affect what happens here. Systems like this will have to sort of justify what they can do. I mean, there need to be applications which provide enough of a benefit to go to the trouble of sticking sensors and that on. And that's that's something that we'll all see whether that pans out or not. Ritul.
Curiosity. What is known about the implications of being exposed to 4 watts of power?
Well, we issue everyone in the lab with a cup, and you're welcome to come and visit.
Look at what he does to his friends. Look at what he does to him.
Yeah,
I don't know your little distant.
Why do you think he's moving the markets up?
You know, I don't know. So the FCC tells us this is all fine. I have nothing else to say. There are a lot of readers around who probably don't know.
There's 300 watts of much higher frequency RF coming from those light bulbs.
The light bulb is producing more energy than it receives.
Look what's happened now. Yeah, so Rutal, I don't have anything sensible to say to that other than, you know, this is the situation, and yeah, your mileage may vary.
I imagine that has mostly implications for the kinds of applications you would build. You know, if it's like in-home activity recognition may or may not be feasible just out of that field, because that would mean constant exposure.
Yeah, well, so the implantable things would really come first. And you might be able to do some of these applications with significantly lower power. This is just the way RFID readers work today, and what you need to be able to get things to work on edge. But you don't need to worry about your cell phone.
Let's call it good there.
One last question. What are you making those poor people eat?
Well, this is Vegemite. I love this. This is like this. It's like a lab eating Vegemite.
Do you provide the spoon? Because that's really sending the wrong message.
I know. Yes, this is not how. Yeah. For the rest of you, this is not how you normally eat Vegemite. This was a going away present. The lab ate Vegemite.
Yeah,
it's great.
All right.
Okay, thank you.
Again, David.